Okay, we have started with the function r of t. We've broken it into two functions and used those two functions to construct a graph of the path of this function, sort of like going up a curving roller coaster or climbing along the coil of a spring. We ask what's the derivative of this vector function and what does it tell us about this path? Well, remember that r of t was cosine of ti, etc., the function you see in front of you here. And it's easy to take the derivative of this. We don't even have a chain rule to worry about. We see that the derivative has I component negative sine of t, 2 cosine of t for the j component, and just plain old 1/2 for the k component. What does this tell us? Well, for example, at t equals 0, pi over 2, pi, 3 pi over 2, 2 pi. Let's get that up on the screen where we can see it. What's our r vector? R is going to be, well, t equals 0, the sine of t is 0. This is going to be then 2j. At pi over 2, we're going to have negative I, 2j plus 1/2 k up here. The 1/2 k is always going to be there for any value of t. So we have minus I plus 1/2 k at pi over 2. At pi we have negative 2j plus 1/2 k. 3 pi over 2, we're going to have I plus 1/2 k. And at 2 pi, we're going to be back to the same vector we had at t equals 0. What does that tell us about our path? Well, let's get our path up here and hopefully get these values on screen. Here's our path again. T equals 0 point is here. The r vector is 2j plus 1/2 k. That would be a vector that comes over 2 units in this direction and up 1/2 a unit in this direction. I should use a different color here. Okay. If we come over 2 units and up 1/2, we get a vector something like this. At t equals pi over 2, we have negative I plus 1/2 k. Now the t equals pi over 2 point occurs around here, and we're up on the vector here. The negative I direction is going to be parallel in the direction of the negative x-axis, and the 1/2 k is going to come up like this, and our vector, I'm going to extend it a little bit, our vector comes up in this direction. Now both of these vectors appear to be plausibly tangent to the curve. At the t equals pi point, which corresponds to the point along the negative x-axis, that would be here, the vector is negative 2j plus 1/2 k. Well, negative 2j would be back this way, plus 1/2 k would be up here, so our vector might look like this. And at the 3 pi over 2 point, I would be in the positive x direction. The 1/2 k would again be upward, and we would end up with a vector in this direction. This is complicated a little bit because that vector is coming at us. It doesn't look as long as it is, and also interferes with the labeling here. By the time we get to 2 pi, we're back to 2j plus 1/2 k vector, which would be the same as this vector, moving parallel to this vector. The magnitude of r, just looking at these sample points, the square root of 2 squared plus 1/2 squared is the square root of 4 1/2, which is about 2.2. Square root of 1 and 1/2 is about 1.2. Actually, the square root here would be about 2.1, but let's not worry about that. And make the same mistake again. We get magnitude 2.2, 1.2, 2.2, where the 2.2 should really be 2.1s, I think. The point to be made here is, where's this function, where's this vector moving the fastest? Well, it's moving the fastest when it's in the moving in the y direction. Okay, when we're around at this point and this point, and that makes sense in terms of our original ellipse. We're moving faster when we pass this point than we are when we pass this point, because when we pass this point we're moving in this direction where the distance is greater over a given time period. When we pass this point we're moving in this direction where the distance in a given quarter cycle is somewhat less. So that by looking at this function and just evaluating it at a few points, we see that the motion along this ellipse is, or this helix, is speeding up, slowing down, speeding up, slowing down as we move around. We can consider the magnitude of our r of t function, and that's going to be what? Square root of sine squared of t plus 4 cosine squared of t plus 1/4. Just taking the sum of the squares, applying the Pythagorean theorem to the r prime function. This function could be analyzed. We could take its derivative, find its maximum, its minimum, and verify that actually these are maximum and minimum values of the magnitude. Once more, we're not going to go into that calculation. It's really too messy to fool with, but in principle it's a fairly easy thing to do.